All right, we're gonna go ahead and get started here. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover everything you need to know about medical device cybersecurity, presented by Senior Software Engineer Eric Blankenhorn. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Eric will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO178 support, a FIPS 140-3 certification and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as WolfBoot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now, I'd like to turn it over to Eric to discuss everything you need to know about medical device cybersecurity.
Excellent. Thanks, Emma. So today we'll be looking at how wolfSSL products can help secure medical devices and some of the use cases we've had in this industry. For our agenda today, we're going to look at the medical device landscape and some of the attacks that have happened recently. We'll go over the regulatory landscape, some of the security trends that we've seen, the use cases that wolfSSL has seen from some of our medical customers, and then we'll go through a couple of wolfSSL solutions that can be used in medical devices. Our TLS library, wolfSSL, wolfCrypt FIPS, wolfentropy, our secure bootloader project called wolfboot, and wolfSentry, which is our embedded IDPS solution. So as Emma mentioned, we've got over 5 billion secure connections. We've been growing over the last 20 years. Got over 2,700 OEM customers and partners, partners that include device chip manufacturers and OS vendors. wolfSSL likes to focus on three main areas. First, it secures data at rest using wolfCrypt, ensuring protection when data is stored and not actively transmitted. Second, wolfSSL secures data in transit, typically through protocols like TLS or SSH. While commonly used over TCP, this can also occur over various other transport mediums, including scenarios where TLS runs over memory buffers without traditional transport layer, and also things like UDP, Bluetooth, etc. Finally, wolfSSL handles secure firmware updates by combining wolfCrypt with a secure transport medium and a secure bootloader to guarantee the integrity and authenticity of these updates. So this slide presents an overview of our current product lineup. Our core offering is, of course, wolfSSL, which can be combined with wolfCrypt for either crypto-only functionality or a full TLS stack. For wolfCrypt, we offer FIPS 140-3 validation. And with the validation process recently completed, we also have things like a DO178 certification for avionics and an asynchronous crypto module designed for server-side use with cards like Cadmium, Nitrox, Intel Quick Assist, things like that. Beyond our core products, we also provide Wolf MQTT for client-side MQTT implementations, Wolf SSH for SSH client server libraries, Wolf TPM for TPM 2.0, wolfboot, our secure bootloader. Additional solutions include wolfSentry, our embedded IDPS, wolfentropy for random number generation, and our newest project, wolfHSM. We also offer commercial support packages and consulting for the curl project, including Tiny Curl, a stripped down version of curl for resource constrained devices. While the wolfSSL library is written in C, we offer language wrappers for various platforms. Users can integrate wolfSSL with Java through JSSE, JCE providers, or even a direct JNI wrapper. We also support users working with C Sharp, Python, and JavaScript. So let's jump in. The medical security landscape presents several concerning statistics. As of 2023, US hospitals housed around 190,000 distinct medical devices, with an average of 10 to 15 connected devices per patient bed. This number is projected to continue growing, with more devices incorporating smart elements. A 2020 survey by the Palo Alto Network shed light on the current security posture, revealing that 51% of healthcare organizations' threats involved imaging devices. A significant 83% of these medical imaging devices operate on unsupported or legacy operating systems, which inherently harbor more potential vulnerabilities. Additionally, 72% of network VLANs are mixed IoT and IT networks, making them more susceptible to attacker ingress through insecure IT assets. Furthermore, 98% of all IoT device traffic is unencrypted, highlighting substantial opportunities for enhanced security measures in the future. The 2025 healthcare breach report indicated an 88% increase in medical device attacks in 2024, alongside the emergence of several significant medical device vulnerabilities. Notable examples included Urgent 11, a set of 11 zero-day vulnerabilities in the TCP/IP stack of VxWorks, which were found to impact numerous medical devices. Another identified vulnerability was Slemtooth. It's a Bluetooth SDK stack vulnerability, also discovered in medical devices. The reporting and public awareness of these vulnerabilities are becoming more prevalent. Ransomware attacks have also surged, with instances like WannaCry, well, remember that, impacting hospitals and medical devices globally. The healthcare industry has become an increasingly attractive target, partly due to a historic lack of security focus. Consequently, these attacks are becoming more frequent and financially detrimental to the medical industry. So, with increased complexity and connectivity in medical devices, the layers of software and potential attack vectors have multiplied. While simple, unconnected devices pose fewer security concerns, today's network devices transmit data to the cloud, hubs, and other devices, necessitating the protection of patient data. Implants introduce a new attack vector, and the ability to update devices requires safeguards against malicious firmware updates. Even the FBI has issued recommendations to safeguard the medical device industry, emphasizing that outdated software in these devices presents an easy target for malicious actors. Consequently, without enhanced security measures, the strength of your network is compromised by its weakest device. Due to these security flaws in medical devices, the FDA established the Digital Health Center of Excellence, which offers guidance on cybersecurity for medical devices. A significant reference throughout our presentation today is a guidance document initially released in 2022 and has been subsequently updated, which we'll cite in the upcoming slides. Uh, FIPS 140-3 is a critical standard frequently discussed among medical customers and is considered a best practice for adherence to HIPAA security rules. Its use is mandated for all Department of Defense or government projects, which require a FIPS validated cryptographic library. While sometimes viewed as a simple checkbox, FIPS compliance can be a significant hurdle. It's important to distinguish between genuine FIPS validation and misleading terms like designated for FIPS or FIPS compatible, which vendors may use but are generally insufficient and often flagged during audits. Current FDA guidance, as outlined in previously mentioned documents, recommends selecting industry standard algorithms and protocols, ensuring appropriate key generation, distribution, management, and protection, and implementing robust nonce mechanisms. This emphasizes the importance of utilizing modern industry standard protocols over outdated or vulnerable legacy options. The guidance specifies the use of current NIST recommended cryptographic standards such as FIPS 140-3 or NSA Suite B or equivalent strength cryptographic protection. This is where FIPS plays a crucial role in the FDA guidance. So, Section 3305 of the Federal Omnibus Bill mandates that all new medical devices comply with specific security requirements. This involves a comprehensive plan for monitoring, identifying, and resolving vulnerabilities and exploits. It also implies a mechanism for updating devices to address these issues as necessary. And an SBOM must also be provided to track software packages within the device. So next up, let's look at some of the use cases that we've seen from wolfSSL's customers and some of the security trends as well. In our first use case, wolfSSL and wolfboot were utilized in a remote patient therapy and wireless neurostimulation device. This project used the ThreadX operating system on a pair of STM32-based hardware platforms. Our engineers were able to help this customer achieve their power and memory goals and simplify their software packaging as the same code base could be used across the product lineup. The next project we'll talk about was a patient smart bed, which had requirements for certified cryptography. This customer was able to meet their FIPS requirements without changing their application code that was implemented with the OpenSSL API by plugging in our wolfcrypt FIPS module using the wolf provider interface. This allowed the customer to easily update their existing commercial software to a package that could be used in restricted government environments. This project used embedded Linux on an NXP IMX6 target. Moving on, we'll examine a patient care monitor project that utilized both FIPS certified wolfcrypt and wolfSSH. This project involved multiple operating environments, including QNX, RTOS, Linux, and Windows. Both client and server sides employed SSH, with all communications secured by FIPS certified cryptography. For this particular solution, we developed the wolfSSH server daemon. This project used wolfSSL to secure data transmission from a connected blood analyzer device. The project used an ARM Cortex-M3 device running FreeRTOS. The biggest consideration here was a small memory footprint with a modern TLS 1.3 connection. Our engineers were able to help this customer with a couple configuration tweaks to quickly get the project moving in the right direction. For our next use case, consider an endoscopic surgery device. This product incorporates wolfSSL's Wolf TPM or TPM2 library and wolfcrypt. It runs on a Xilinx UltraScale Plus device with the QNX operating system. The customer leverages the TPM 2.0 module for secure key storage. Initially, there were some challenges processing high volumes of streaming data. However, with the wolfcrypt and the assistance of our engineering team, in fine-tuning the library, we successfully met their processing requirements. In this next project, there was again a need to use the FIPS certified cryptography. There were significant performance considerations in this project. Um, wolfSSL was able to help the customer meet their goals. In this next project, our next use case involves a dialysis machine that integrated wolfcrypt, wolfSSH, and wolfSSL. This system, built on an NXP IMX6 device, leveraged the CAM hardware crypto acceleration for AES XTS and hashing. While running on the Green Hills Integrity OS, we faced some engineering challenges integrating wolfSSL with the CAM device, particularly on integrity. Some custom driver development was necessary, but we ultimately delivered a successful solution to the customer. A little bit more about this. In this scenario, leveraging hardware cryptography rather than the wolfcrypt software cryptography resulted in direct calls to the hardware, leading to improvements in both performance and reductions in code size. Benchmark data for a lot of these projects, illustrating the performance differences between the hardware and software cryptography, is available at our website, wolfSSL.com, at the benchmarking page. Another application involves a portable defibrillator and ventilator. In this instance, wolfSSL products utilized are wolfcrypt FIPS, wolfSSL, and its Python wrapper, actually. The system operates on an NXP IMX7 device running Yocto Linux. To meet the FIPS requirements for validated cryptography, this customer opted to compile open source components such as Nginx, Python's URLlib3, and Python's WebSocket client against wolfSSL instead of OpenSSL. And an embedded connected insulin pump utilized wolfSSL for TLS, operating on an STM32 device with ThreadX as the OS. This customer selected wolfSSL due to its well-supported library and small footprint, which wolfSSL helped optimize to meet their target requirements. In a recent project, we successfully deployed wolfcrypt FIPS and wolfSSL within a connected device hub built upon the NXP IMX7 platform. This particular use case highlighted the importance of robust security as it was subject to the FIPS 140-2 compliance requirements. A core challenge for a customer was to implement secure authentication for this hub. To meet this need, we leveraged TLS 1.3. wolfSSL has been at the forefront of TLS 1.3 adoption, offering full support for this standard since its official standardization in 2018. Our implementation ensured that the hub's authentication mechanisms were not only secure, but also fully compliant with the required FIPS 140-2 standards, providing the customer with a high level of assurance in the security of their connected device. So this project used wolfboot to allow the device to securely load a firmware image with free RTOS and the application. The cool thing about this project was that they were able to use the existing port of wolfboot for the Zinc Ultrascale, which really highlights the adaptability of the bootloader project. And our final use case, this involves a tablet. It was utilized during organ transplants. This device leveraged wolfcrypt on an NXP IMX8 platform, again using the CAM hardware crypto. Our engineering efforts here were concentrated on enhancing the AES and ECC performance to optimize throughput. We also had to modify wolfSSL to ensure compatibility with the CAM on QNX. And the tablet's role in this scenario was to monitor other devices throughout the organ transplant procedure, with wolfcrypt securing both data in transit and data at rest. So let's kind of summarize some of the things we talked about in those use cases. So a review of these use cases kind of reveals several security trends. Many customers are seeking to migrate to TLS 1.3, secure data at rest with encryption, and utilize secure enclaves, key stores, or TPM modules when available, adding robust security layers. There's also a focus on leveraging hardware cryptography for performance acceleration and enabling secure firmware updates and secure boot to patch vulnerabilities and extend the device lifespan. Additionally, FIPS certified cryptography, including an approved source of entropy for random operations, is often required for VA, government, and even some non-government contracts. So next up, we'll cover some of the wolfSSL solutions that can help secure these types of medical devices. The first one of these being wolfSSL, which is our TLS and DTLS stack. So wolfSSL offers TLS 1.3 and DTLS 1.3 support, boasting a small footprint with typical build sizes ranging from 20 to 100 kilobytes, depending on the build, compiler, and optimization level. Runtime memory per session is 1 to 36 kilobytes of RAM. This makes wolfSSL approximately 20 times smaller than OpenSSL, making it ideal for IoT and embedded devices. It supports over 40 operating systems out of the box, from Windows, Linux, and Mac to various RTOSes and even bare metal environments. An OpenSSL compatibility layer is available for migration, implementing thousands of the OpenSSL functions internally. wolfSSL has been ported to several web servers also, including Apache, Nginx, Lydie, and Mongoose. It also provides hardware crypto support for numerous platforms with easy expandability. WolfCrypt has achieved 140-3 validation, and wolfSSL has been integrated into various open source packages, such as WPA Supplicant for medical devices, requiring FIPS validated crypto libraries for Wi-Fi authentication. So this may not be coming up for everyone yet, but let's talk about it now. When planning for the long life of medical devices, it's crucial to consider the emerging threat of post-quantum cryptography. Um, HIPAA PQC requirements are anticipated in the near future, making it imperative for manufacturers to begin testing PQC solutions now. All wolfSSL solutions are PQC compatible, offering a proactive approach to security. This includes wolfSSL for TLS, ensuring secure data in transit, wolfCrypt for robust data encryption at rest, and wolfboot for secure firmware updates, all of which can be adapted to support post-quantum cryptography algorithms as they become standardized. So now let's talk a little about our FIPS solutions that can help you meet some of your regulatory requirements. So wolfSSL has two active certificates for wolfCrypt FIPS on 140-3, certificate 4718 and 5041. We have a couple more FIPS certificates pending. Those are going to allow us to help other customers down the road. FIPS 140-3 certs are valid for 5 years after approval with options for extensions. This diagram kind of shows where the wolfCrypt FIPS module fits in relation to wolfSSL and the application. So we've drawn our FIPS boundary around a subset of wolfCrypt itself, which means that the TLS code is out of the validation scope. This was done by design, since most of the vulnerabilities and bugs that we find and fix are in the TLS layer, not necessarily down in the crypto layer level. So a FIPS customer can still use the same FIPS validated library from release to release of wolfSSL, the TLS stack, still updating the TLS part of that library without invalidating their certified application. Additionally, we offer a GPL license version called FIPS Ready, which can be used to develop software using the same FIPS constraints. This is useful for projects that have not identified a specific operating environment yet, or may be pending an approval or acquisition process. When the hard requirement for FIPS certification is finalized, it's just a matter of linking in the proper FIPS library. When it comes to new validations, there are two primary solutions. One option is to add a new operating environment, or OE, to an existing certificate. An OE is defined by the combination of the operating system, the processor platform, and the wolfcrypt version. Alternatively, a rebranding validation can be performed where the certificate is rebranded under a customer's name. If necessary, the module boundary can then be either expanded or reduced. While this process can sometimes be more complex, it may be required depending on the specific FIPS requirements and the project timelines. Ultimately, the chosen approach is influenced by the project scope, whether the platform is standard or non-standard, and the current timeframes observed for the lab and the CMVP. So we began this by discussing a little bit about the engine and provider solutions, highlighting a quick method for applications utilizing the OpenSSL API to transition to wolfSSL and wolfcrypt certified FIPS solutions. This is particularly relevant as many OpenSSL APIs, which may currently rely on FIPS certified cryptography, are expected to fall out of scope or move to a historical list soon. The transition is straightforward. Simply link in the new wolfcrypt FIPS solution, allowing continued use of the OpenSSL APIs, while all underlying cryptography shifts to the wolfcrypt FIPS library. Alternatively, the compatibility layer offers another option, maintaining the OpenSSL API within the application, but remapping those calls to native wolfSSL APIs. So this approach offers the advantage of bypassing most OpenSSL specific vulnerabilities and leveraging wolfSSL's highly tested TLS stack and cryptography. Another solution from wolfSSL is wolf entropy. This is our software-based true random number generator. This project utilizes CPU jitter to generate high-quality entropy. This solution is focused on devices where a real hardware random number generator is not available. So even older platforms can be updated to use wolf entropy. The only requirement is that the hardware provides a nanosecond timer. So another critical feature for medical devices are secure firmware updates. Given that all software inevitably contains bugs and vulnerabilities, a mechanism for updating software to address these issues is essential. Firmware updates can also be utilized for things like rotating keys and certificates, which can potentially extend a device's lifespan in the field. While firmware updates are beneficial, secure firmware updates are even more advantageous given, especially in life-critical applications, as they allow for authenticating the source of the binary blob and detecting any tampering. As you'll recall, the FDA guidance document had recommendations that devices should be capable of being updated in a secure and timely manner. So our secure bootloader solution, wolfboot, offers a lightweight, portable, and generic secure boot. It's designed to fit into almost any system and has been ported to numerous platforms. wolfboot prioritizes safe coding practices and avoids dynamic memory usage. It utilizes a dual bank update mechanism featuring a primary partition for firmware, an update partition for new updates, and a small swap section for use during the update process. So this solution is the solution is interruptible, allowing a fallback to the original image if the power fails or an issue occurs during the update. wolfboot also includes protection against downgrade attacks and a rollback mechanism. This allows the system to revert to the previous image if the application determines an update is invalid after completion. As an OS agnostic bootloader, wolfboot supports bare metal and various RTOS environments. While no specific hardware is mandated, wolfboot can leverage hardware assisted features provided by the platform. So intrusion detection can be interesting in the context of medical devices also. Considering that earlier statistic, that 72% of healthcare VLANs integrate both IoT and IT assets, an attacker could easily compromise an IT asset. Therefore, actively monitoring devices with a firewall-like solution to detect ongoing attacks would be advantageous if medical devices are exposed on such networks. And IDPS offers benefits such as detecting malicious activity through static or dynamic rules. When malicious activity is detected, the application then receives events that can be used to log historical events, send alerts, or even trigger other customized actions. So to help facilitate this, we wrote wolfSentry, which is a universal dynamic embedded IDPS. At its core, it features an embedded firewall engine, both static and fully dynamic, with optimally efficient lookups. wolfSentry is dynamically configurable and can arbitrarily associate user-defined events with user-defined actions, contextualized by connection attributes, tracking the evolution of the network transaction profile. Testing is a huge part of wolfSSL, of a wolfSSL engineer's responsibilities. So let's take a moment to recognize this effort. Developing our products is only part of the process. We also prioritize extensive testing measures to maximize security and minimize vulnerabilities. This approach benefits our customers by reducing the frequency of updates and crucially preventing crashes, which in a medical device could be catastrophic. We conduct comprehensive testing year round and are constantly expanding our efforts. Our testing ranges from API unit testing to cipher speed and algorithm testing. We utilize various static analyzers, including Coverity Scan Build and Facebook's Infer. Memory error detection is performed with Valgrind and fsanitize address. To ensure real-world compatibility, we nightly test our customers' build configurations with a range of different compilers. Every line of code entering our repositories undergoes peer review. Additionally, we incorporate third-party testing and fuzz testing with over 6 different fuzz testers. All these tests are integrated into a continuous integration cycle managed by Jenkins. A little bit about our software development process, as depicted in this slide. It centralizes around the source code, right? So on the left, specifications lead to software design documents, which are integral to both API testing and implementation, as well as API documentation on the right. Module and algorithm verification is another crucial step performed using our internal tools, NIST testing tools, our validations, and various certifications. So another thing that makes wolfSSL stand out from other cryptography libraries is that we offer up to 24/7 support packages. Here are 4 different packages: basic, standard, premium, and 24/7. The benefits of each are listed out here. One of the huge benefits that I'd like to point out here is that our premium and 24/7 customers can actually give us their wolfSSL build configuration, and we'll add that to our nightly tests. That ensures that any future releases of wolfSSL are going to be built against your project. The other important thing to point out there is that the higher packages include FDA audit support and even longer term support. And of course, we always offer free pre-sale support if you just email us at support@wolfssl.com. We also offer a Kickstart program. This is the quickest way for you to quickly get your hardware and build environment supported by wolfSSL. It's usually about a week to get the library ported to your tools, OS, and hardware. That may or may not include validation if it's already something that we have on our certificate. It's a great way for you to free up your engineering resources to focus on what you do best. So let's quickly review why our customers choose wolfSSL as for their most critical security projects. So they choose us for our expertise and our industry expertise. We offer commercial support so we can help you get up and running with integration assistance. We have a wide breadth of platform OS and compiler support, which means that it will just work in your environment. We can also help with a Kickstart consulting project and get wolfSSL running in your environment as well. We have low memory use and small footprint size, modern protocol support up to TLS 1.3, FIPS validated cryptography, hardware cryptography support, as well as support for secure elements and TPM 2.0 modules. We are the best tested crypto and TLS implementation available in the market today. Our full product suite is available to help secure your medical device project. Hopefully this was helpful to give you an idea of some of the places wolfSSL is used in current medical devices and how we might help out in future medical devices. And with that, let's open it up for questions.
Wonderful. Thank you, Eric. We'll jump right in. Are you using SAE J3101?
Yeah, so that's one of the specifications that kind of flows along the same lines as some of the FIPS standards. So I have to review that with some of our business directors, whether we support that in particular. But if it's not on the list now, it's certainly something we could do.
Wonderful. What does IDPS stand for?
Sure, that's intrusion detection prevention system. I guess I should have put that in the slide.
Uh, do you see much difference between NIST 2 and the European CRA specs?
Hmm. So they have moved so that the European regulatory bodies and the US regulatory bodies have tried to coordinate a little bit better. And so we have seen some of those standards start to mesh up from one to the other. So we are capitalizing on that. And we have had customers that have found our FIPS 140-3 solutions to fully support all of their requirements in European standards. So I think that's kind of where we're going with that question.
Wonderful. I think you mentioned it, but is the Wolf DTLS parentheses like Wolf SSL library available in the open source community? And if so, is it licensed via GPL?
So that's one thing. So Wolf SSL is actually dual license, right? So we have our GPL code out on GitHub. And then we also offer commercial licensing for customers that are, obviously not going to be releasing their source code, so they can't use GPL code. So they would come to us for a commercial license. And specifically the DTLS, yes, the DTLS library, the Wolf SSL library includes support for DTLS all the way up to 1.3 of that specification.
Perfect. Does Microsoft uh EF EFI sign Wolf boot?
Um, I don't know if we've had a customer with that requirement yet. So I guess you mean for using Wolf Boot to boot up a Windows system, OS system. Um, I would have to circle back with the team to see if we've had anybody with that requirement yet. However, most of the times we've used Wolf Boot has been in the context of embedded applications, which obviously could be some type of Windows IoT or maybe an older Windows CE device. But it's an interesting question. I'd have to loop back with the team on that. Maybe you could ping us at that address on the screen now.
Wonderful. Is FIPS 140-3 actually required by the FDA?
So, not FIPS 140-3 specifically, but considering that the sunset of 140-2 it's mostly happened, 140-3 is a better solution given how long the medical devices exist in the field. And of course, all VA contracts and government entities are going to have those FIPS requirements. And so they're going to be updating those to 140-3 also.
Wonderful. How long does it take to get a new FIPS validation?
Hmm. It's a good question. So it's kind of hard to answer that with a firm number. Currently, uh, we expect it to take approximately 1 to 2 months, but there's a lot of uncertainty around that process. So we'd have to get in touch with you and have a more detailed discussion.
Wonderful. Does Wolf Boot need a separate boot loader to work?
Actually, no. So, I mean, it's designed to be a bare metal bootloader, so it's the single bootloader, but it can work with another bootloader system. So if you have U-boot or some other boot mechanism in your system already, and you're just looking for a way to add secure authentication of the firmware images, that would be a good place to tie in Wolf Boot, and it can be, at any level during the boot process also.
Wonderful. Well, thank you, Eric, for hosting an informative webinar. Thank you to everyone for joining. You can keep up with our upcoming events. Another question came in. We'll answer it real quick. As far as our RTO SEs go, is there any support for Zephyr? I assume we can replace U-boot with Wolf boot.
Yeah, absolutely. We've actually got some examples out there. Of course, the bootloader doesn't care what the image is, if what operating system or applications on the image. So it's agnostic to that part. But we actually do have quite a few Zephyr examples in the repositories, including wolfSSL, of course, MQTT. I think there's a Zephyr SSH example also. So those are all available in the repositories.
Wonderful. All right, back to our closing out. You can meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfssl.com. Thank you again, and we look forward to seeing you on August 27th for our webinar on WolfGuard, FIPS 140-3 enabled WireGuard. Thank you all.